Right, yeah. Hi everyone, I am Rohan Bejal from University of Washington, and today I'll present our work on long-range navigator, extending robot planning horizons beyond metric maps. So as we know, these traditional autonomy stacks have limited range cost maps, which can often lead to myopic decision making when you need to travel to far away goals. Like in this case, the robot doesn't see the wall, heads straight towards it, and ultimately gets stuck. We here are going to talk about long range navigator, a system that is able to leverage visual information present beyond the range of the cost maps to enable more intelligent decision making. Here in this case, the robot can pick out a good direction and avoid getting stuck. The central question we are tackling here is how do we enable robots to make long horizon navigation decisions while leveraging only local sensors without global maps. There's quite a bit to unpack here. So let me give a brief overline of the timeline. I'm going to talk about the problem definition, the pitfalls of the autonomy stacks or the heuristics, our main insights on using these visual affordances, a brief overview of the LRN system, and importantly, how do we make data collection scalable for our problem? So let's talk about the problem. The robot is operating in an unknown environment. It needs to get to a goal somewhere far away, but it has access to a local cost map only. And we want the total path traversed by the robot to minimize some kind of objective, like traversal time, minimize interventions, something like that. We follow a traditional perception planning control stack. So the perception system takes in camera images, depth images, maybe other sensors, and creates this kind of cost map. Anything outside the range of the cost map is termed unknown space. The planner takes in a frontier node at the edge of the cost map and plans to it using A-star search. And finally, we use something like MPPI to follow this plan. Now, coming back to the question, the long-range navigation problem, what's challenging here? Notice that our goal is outside the range of the cost map. So this problem is hard to solve optimally, but we can have some good heuristics to guide the robot. So the natural question then becomes, how do we guide the robot using things like frontier nodes or heading directions? And I'll explain that more. Here's a simple idea. Pick frontier nodes. Frontier nodes are these like blue nodes at the edge of the cost map. Pick frontier nodes that are closest to the goal in, say, Euclidean space. And that way you can get these kinds of frontier nodes which are heading in the direction of the goal. It's quite intuitive, works in a lot of cases, but as we'll see, it can lead to some not so intelligent decisions. And that's essentially you're considering all of the space outside this cost map as uniform cost. You're not differentiating between that. So let me show you some pitfalls that we face. I'm going to use Spot in this urban environment as an illustrative example. The Spot has a local cost map which does not see the wall right now. The goal is behind the wall, and the heuristic leads Spot to like head straight into the wall. It gets too close to it, and ultimately it's unable to recover. But notice that while this wall is not present anywhere in the cost map over here, it's actually visible in the image, in the visual feed of the robot. So to summarize some key observations in these failures, the frontier nodes are what guides the robot, and secondly, we have visual information present which we are not utilizing well. So the question is, can we just use that visual information to predict better frontier directions for this long-range navigation problem? And that's basically our key insight, that the robot can reason further by identifying distant, affordable frontiers as intermediate goals. Let me talk more about these frontiers now and explain it. The frontier prediction problem is as such. We want to predict good frontiers at the edge of the cost map. So these are these blue circles on the left, and this could look something like these blue circles on the right in the visual feed. So this frontier could be considered nice because it's traversable, and ultimately it would allow the robot to maybe head to that opening much further away. But the challenge here is if you want to relate this frontiers at the edge of the cost map to very global information present in the image, it becomes challenging with less data. So instead, we change the problem and we say we want to predict these frontier nodes or frontier spaces directly in the image space. Think of these frontier nodes or these frontier pixels as having some kind of value. This value is broken down as an affordance score and a goal score for like additional context when using as a goal. In our work, we are essentially going to focus on learning this affordance score while relying on simple rules or heuristics for the goal score, but in future work, it could be, you could learn it too. Now, what do we mean by affordable? It's weird math, but essentially, an affordable frontier is something where you can easily get to the frontier and there's a likelihood of continuing beyond it. So imagine traveling on a long trail and it goes out into the horizon. A point in your visual horizon would be a good point at the trail because you can follow the trail and it's likely that the trail continues beyond that. But if you have a wall, a frontier on top of that wall is not a very smart idea because you can't go through the wall. For the goal score, we can consider a simple rule like consider the angle, the heading direction of the goal and the heading direction of the frontier, and its high score if it's close in terms of the angle. So now the question is, how do we get these labels for supervision of the signal of the system? And the first version is a little bit unsatisfying, which is manual human annotation, but I'll later talk about how we can make this more scalable. For clarity, we have these images and the human marks these lines in the image as affordable frontiers. We do a small blur around them to get scores for supervision. Let me explain the LRN system as a whole now. So the LRN system will take in camera images and pass it through a SAM model. Then we train this small deconvolution network to predict these affordance heat maps. The trained system would look like this. The red score means high affordance, while as you go darker blue, it's lower affordance. So how do we use these predictions for our ultimate goal of navigation? We can use camera intrinsics and extrinsics during deployment to convert pixels to heading directions in the 3D world. So we can convert those scores to actual heading directions. For the goal score, we consider a Gaussian around the goal direction. And lastly, in order to maintain some kind of temporal consistency across time, we have a Gaussian score on the prior heading direction also. We combine these scores and ultimately we can decide on a frontier direction. Imagine that same scenario we saw with Spot, but now we add LRN. LRN is able to find these affordable frontiers in image space and adjust the heading that the robot takes to enable more intelligent decisions, and it avoids getting stuck and is able to reach the goal. Okay, so we ran LRN and multiple baselines in 3 environments. This is a nighttime scenario where notice how the goal heuristic in orange heads straight into the bushes and gets stuck, so it leads to an intervention. But the LRN is able to follow this nice frontier at the road and not get stuck. We saw similar behaviors in some other environments also, and I'm going to show you some more statistical results we have for these environments. But let me explain some of the other baselines we tried for this. One is the traversability plus depth baseline. So you take a depth estimation model and a traversability estimation model, and you combine these scores to get these hotspot scores. The intuition in this baseline is that an affordable frontier is something that's far away from the robot, but also it has to be traversable. The second baseline we try is Nomad. This is a visual navigation system which conditions on the goal image and uses a topological graph for navigation. So we ran each of these methods for 5 times on each environment, and we can see statistically significant benefits of LRN for traversal times as well as leading to no interventions. There's a point about the helipad course leading to higher traversal time, which I'll get to towards the end. Also, a quick note that I'll put regarding Nomad is systems like Nomad aren't traditionally designed for these waypoint navigation scenarios that we see in off-road environments, but I think doing some of these tests does highlight the fact that in waypoint navigation, and especially unstructured environments, having a goal image as context is usually not enough. So you need more information in terms of geometry, or if you want to use a system like Nomad, maybe you need a more dense topological graph. I'm going to skip this for now. Maybe you can see in the website. So LRN leads to benefits, but as we saw, the data generation process was human labeling, but that is obviously tedious. So is there a way we can make it more scalable? And this is what I'll talk about now. Notice that we have these kinds of videos from either the robot on the left or people walking in environments in a vlog style video. And hopefully there's something useful we can leverage here. And the key insight is that we can extract useful navigation priors like trajectories or our affordance heat maps via video point tracking. So let me explain this a little more. Video point tracking methods are able to track points in image space across a video, and these models have gotten really good over the last few years. They've also been used significantly in manipulation to make policies robust, but haven't been explored as much in navigation. So how do we make it work for our case? Notice that in these videos, since we want the labels for affordance heat maps and image space, we ultimately want to know where the robot was or kind of where our feet were in the image space. So what we can do is start a video from the end, mark some of these points close to where our feet would be, and run the video tracking in reverse. You can periodically reinitialize it to get this kind of trajectory, like you'll see on the left. Now, another cool thing about these video tracking models is that they'll also tell you when a point becomes occluded. So imagine the point towards the end. As you track it back and back and back, at some point it'll get occluded. And that's a nice time to say that, okay, this is the boundary of my visual known space versus unknown space. So I can mark that as an affordance supervision signal. So the red part, yellowish part is like a score of 1, and the other part is not an affordance. We walked around in parks and collected around an hour of data and used our procedure to extract these affordance labels. And notably, all our experiments on the Spot robot were done with these auto-labeled affordances. I will like to highlight some undesirable behaviors or limitations of the system. So this is the helipad course we were working on, and this is kind of an open field, and we see this kind of wandering behavior from the robot. There are multiple factors that can lead to this, either somewhat incorrect predictions, or maybe there's more tuning required for the previous goal heading to ensure more temporal consistency. And also, in our current system, we are not utilizing any form of depth for the purpose of visual affordances, so there can be some ambiguity because of the depth also. I'd like to summarize with the main takeaways that I'd like people to take from this talk. So we see that map-based navigation is myopic beyond the map, and it can lead to some not so intelligent decisions. But LRN is able to extend the planning horizons via these learned visual affordances. But finally, note that LRN is still a heuristic for navigating unknown space, and LRN can tell you not to head into a wall, but LRN does not necessarily know whether going right or left will lead you to a dead end. So it's something to keep in mind because you just don't have the information there. And that's it. This is a summary of the takeaways, like I mentioned, and that's it for my talk. Thank you. Happy to take questions.
All right, thank you very much. So we're going to questions before we break?
Do you see any issues with temporal stability?
Right. So at every instant, the LRN will predict some affordance heat maps and use it to like compute the scores. Now, the training does not take into account any kind of temporal consistency. It just takes an image and produces an affordance score. So in order to ensure that the robot makes smooth decisions or like is temporally consistent, we added the prior heading cost to the LRN system. Let me see if I can show it to you really quickly.
So essentially like a low-pass filter-ish?
Kind of, yeah. Like basically whatever heading you took at the last time, you can also put some Gaussian cost around it to like avoid this kind of switching behavior.
All right, so we're going to start up again at 2 o'clock. We'll start off with some keynotes. So try to get here, 1:55 or so we're not talking through all the keynotes. But yeah, we'll see you guys at 2 o'clock.
Thanks, Eric. Thank you. Try not to drop this.
How many times this thing is like